Hey everyone, and welcome to this explainer. Today we're unpacking what has absolutely become the ultimate framework for any aspiring generative AI engineer. We're talking about RAG, or Retrieval-Augmented Generation. If you've ever wondered how ChatGPT-like applications manage to securely access private, real-time knowledge without missing a beat, well, you are in the exact right place.
To really get why RAG is such a game changer, we first have to ask a pretty simple question. What happens when an AI is just forced to guess? You see, the core limitation of large language models is their knowledge cutoff. They get trained on data up to a very specific point in time, and after that, they're essentially blind. When they lack specific private data, they tend to just confidently invent facts out of thin air. We call this hallucination. And honestly, it's not a bug. It's literally just how LLMs work when they don't have the right context.
So here's our blueprint for today. We're going to cover the AI knowledge problem, the core RAG pipeline, embeddings and vector DBs, semantic search, classic versus agentic RAG, and finally RAG versus fine-tuning. Let's get right to it.
Okay, Section 1, the AI knowledge problem and the limitations of LLMs. This whole issue fundamentally stems from the fact that language models are incredible at reasoning, structuring, and writing, but they are actually terrible at knowing objective truth without some external help. Their knowledge is totally frozen in their weights.
I absolutely love this analogy because it perfectly illustrates the solution. RAG is basically a street-smart alternative to really expensive model retraining. Instead of forcing the AI to painstakingly memorize everything by retraining its internal parameters, you just give it a search engine over your own data right before it answers. It's exactly like taking an open book exam. The AI just needs to know how to find the right page fast, read it, and then synthesize a great answer for you.
Moving right along to Section 2, the core RAG pipeline. Let's look at the offline and online flows. To really grasp the architecture here, it's best to just follow the journey of a single data point through these two very distinct workflows. We'll start with the offline phase. This is where we prepare and build up your knowledge base. First, we load the raw data. PDFs, wikis, databases, all that stuff. Next, we clean and chunk that data into smaller, manageable pieces. Third, we embed those chunks into mathematical vectors. And finally, we just store them in a specialized vector database.
Let's actually zoom in on step 2 for a second, chunking. This is a massive engineering decision. If your chunks are too large, your retrieval is going to return bloated context, it'll miss the exact relevant detail you needed, and it totally wastes the LLM's precious context window. But on the flip side, if your chunks are too small, they lose all their semantic meaning, and the AI just gets this fragmented data that makes absolutely no sense. It's a real balancing act.
For all you aspiring Gen AI engineers out there, mastering advanced chunking is how you really stand out from the crowd. You generally want to start with the natural structure of your data, but you can push the boundaries with techniques like contextual retrieval. This is a brilliant tactic pioneered by Anthropic. Basically, you use an LLM to generate a quick 1- or 2-sentence summary explaining where a chunk fits within the broader document, and you prepend that summary to the chunk before you embed it. It's a game changer for preventing context loss.
So that was offline. Now, what happens in the online workflow, like in real time when a user actually asks a question? First, the user submits a query. We instantly run that query through the exact same embedding model to turn it into a vector. We use that vector to retrieve the most relevant chunks from our database. Then, and hey, this is the augmented part of RAG, we construct a brand new prompt combining the user's question with those retrieved facts. Finally, the LLM generates an answer that is grounded entirely in the truth.
All right, Section 3, embeddings and vector DBs, or as I like to call it, searchable math. What's really wild here is how human text actually becomes searchable math. It's the secret sauce of this whole operation.
Enter vector embeddings. An embedding is basically a translation step. It takes human language, whether that's a word, a sentence, or a whole chunk of text, and it converts it into a massively long list of coordinate numbers.
Think of it like a giant, high-dimensional mathematical map of the English language. On this map, conceptually similar words and ideas physically cluster together. So king and queen are close neighbors. They share very similar coordinate numbers. But king and pizza, they have completely different meanings, so they end up on completely opposite sides of this mathematical map.
Now, once you have these thousands of coordinates, where do you actually put them? You put them in a vector database, something like ChromaDB. Unlike a traditional SQL database that desperately needs exact keyword matches, a vector database performs lightning-fast nearest neighbor lookups. Honestly, it's like a librarian who has read every book in the world and understands what you're asking for just based on the vibe and the meaning. They instantly hand you the books that are mathematically closest to your query.
And that brings us to Section 4, the semantic search engine. This acts as the ultimate gatekeeper. In a RAG system, this retrieval engine strictly controls exactly what the generator LLM is allowed to see. Simply put, if retrieval fails, generation fails.
As an AI developer, you've got to choose your retrieval method super carefully. You have keyword search, like BM25, which is highly literal. It's totally perfect if you're searching for exact tokens, think error codes, part numbers, or specific legal IDs. Then you have semantic search, which matches meaning and intent. That makes it ideal for natural language questions where a user might use totally different words to describe the exact same concept. More often than not, the very best enterprise systems actually just use a hybrid of both.
To make semantic search instantly relatable, just think about the Spotify algorithm for a second. Spotify maps the tempo, the mood, and the genre of a song to find tracks that fit your specific taste, even if they're by completely different artists. Semantic search does the exact same thing, but for text. It matches the hidden parameters of meaning to find the perfect contextual fit for your user's prompt.
Let's jump into Section 5, Classic versus Agentic RAG. We need to look at our retrieval workflows and see how this all builds up, because sometimes a simple, single-pass lookup just isn't going to cut it for complex enterprise queries.
This is where we compare classic RAG to agentic RAG. Classic RAG is a linear, stateless pipeline. It retrieves once, generates, and forgets. Agentic RAG, however, turns retrieval into a super dynamic control loop using the REACT pattern: reason, act, observe. The LLM acts as an autonomous agent. It analyzes the query, decides which tools or databases to search, reads the results, and then literally decides if it needs to search again to fully piece together the answer.
But here's the crucial point. While agentic RAG is incredibly powerful, it introduces some serious engineering trade-offs. It buys you amazing multi-step reasoning, sure, but it's going to cost you in much higher latency and increased API token usage. It also creates unpredictable failure modes, like imagine an agent just getting stuck in an endless loop. That means you absolutely need strict guardrails and deep observability to trace exactly what the agent is doing under the hood at all times.
Finally, let's address Section 6, RAG versus fine-tuning. This is without a doubt the ultimate debate in enterprise AI right now. Should you inject knowledge via RAG, or should you just fine-tune the model itself? Here's the breakdown. RAG wins heavily when you need dynamic, factual accuracy. It's way cheaper to update. You literally just drop a new PDF in your vector database, and every single answer is strictly verifiable with citations. Fine-tuning, especially with efficient methods like LoRa, is expensive and it hides knowledge deep inside the model's weights where it really can't be audited. But fine-tuning is absolutely the winner if your goal is teaching the model a specific tone, style, or output formatting behavior.
Oh, and before we wrap up, it is definitely worth noting the absolute cutting edge of this architecture right now: multimodal RAG. Real enterprise data isn't just text, right? It's charts, it's images, it's complex tables. By using models like GPT-4o alongside multi-vector retrievers, we can actually extract summaries of images and tables, store those summaries in our vector database, and then map them right back to the original files. It completely pushes RAG to handle mixed data formats seamlessly. Well, we've covered a ton of ground today, all the way from basic embeddings to complex agentic workflows. Ultimately, RAG is the framework that transforms a language model from a smooth-talking guesser into a grounded, verifiable expert. So, as you go out there and start building these systems yourself, I want to leave you with this one question to think about. Is your AI just smart, or does it actually know the truth? Thanks so much for joining me on this explainer, and keep building.